All right, what you guys have to do is you have to draw the hybrid orbital scheme over and over until it becomes automatic. I saw some drawings there, which I've seen similar drawings on tests, and yeah, they don't look good, some of the drawings. And so you got to make sure that you know how to draw it. So for example, if I drew it like this, one sp2 here, one sp2 here, one sp2 here, how does that look? Does this look good? It doesn't quite look good because, yeah, do you see? What we need is one, if one is pointed to the right, then the other two should be pointed like this?
No.
No.
Mercedes.
It should be, yeah, it should be pointed back like this. And so we're going to draw them like this. You can already see it in the Lewis structure here. These two lone pairs must occupy these orbitals here, and we have a bond here. All right, so what I'll do is I'll go ahead and draw these. Okay, what's the hybridization again?
SP2.
So what does the energy level diagram look like?
It's going to be the S.
Three sp2s and a p for one oxygen here. How many electrons does oxygen have? 6. 1, 2, 3. The fourth one, pair or promote? Promoted. Fifth one?
Wait.
Am I recording? Yeah. Recording. Actually, this is what we need. The other way of thinking about it is we need two lone pairs and two bonds. Do you see that? Two lone pairs and two bonds.
So if it's SP2.
All right, so let me go ahead and draw this out. I'm going to move this since I don't have much room right here in the light. And so you should automatically know how to draw the sp2 orbitals. 1, 2, 3. This looks kind of funny. Sorry, but if this is sp2, and this is sp2, then where's my p?
In the middle?
Yeah, it's in the middle.
Yeah. It's going up, right?
Yeah. Up out of the board, one lobe sticks out and the other lobe sticks in. This is why I kind of drew it squiggly, so I don't want to draw it too. We have two lone pairs, sp2 lone pair, and then we have a single occupied and single occupied here. The other oxygen is exactly the same. And so we got an sp2, this with one electron, an sp2 with a lone pair, and an sp2 with a lone pair. And so now we see one of the bonds, the sp2 sigma bond. It's a double bond, so there's one sigma and one pi. And so where's the pi?
What about the one in the P?
Yeah, that's going to bond here. So we got this p electron here bonding with this p here. And so this is going to be our p pi bond. So we got a pp pi bond and an sp2 sigma.
That's the top view, right?
This is called the top view because how come I call this the top view? Because we're looking at on top of the p orbitals, right? Okay, sorry. Turn this on. So we're looking on top of the p orbitals, which means there's a side view. So what would the side view look like?
So we put it like this.
All we do is we take this and flip it 90 this way.
Can you do that?
Okay, we're going to do that like this. We're going to put an oxygen here.
It's hard for me to like visual to know how to do it myself.
So,
I know how to do the top
all right.
view, but the side view is.
The side view is like this. All we're doing is we're taking this, we're looking on top of the p orbital like this. And all we're going to do is we're going to rotate the p orbital so we look at it in profile from the side. That's all. And so here, the p orbital is going to have a lobe here and a lobe here. Then we have this oxygen over here. The p orbital has a lobe here, a lobe here. We got one electron here, and this is the pp pi bond. And let's draw the sp2 sigma. So sp2 here. This is still in the plane here. sp2 sigma. There's free rotation about sigma bonds, no problem, but is there free rotation about the pi bonds? No. Okay, what about the other sp2s? Now these come out of the plane. One's going to stick it in the front, and the other is going to stick behind, and this is for the two lone pairs here. Something like this. Okay, this we call the side view because we're looking at the side of the p orbital. Uh-huh. The p, okay. P orbitals can bond in two ways. If I look at a px orbital here on atom A, and I combine that with a px orbital on atom B, and I just bring these together, you know, this one to this one, what kind of bond would I create? A sigma bond. This would be called a pp sigma bond. However, the p orbitals can bond in two ways. Now I'm going to look at a p, your book calls this the pz, I think. This is the pz on A, this is the pz on B. Now if I bring these orbitals together, I'm not going to form a sigma, I'm going to form a pi bond. Now the reason it's a pi bond is because I have to look at the internuclear axis. If I look at the internuclear axis here, the overlap is going to contain the internuclear axis. But when I form the bond here, and I'm going to form it like this, here's the atom A, atom B, like this. And so what your book is going to do is they're going to just look at this region here and this region here. So we got electron density there and there, but when I look at the internuclear axis, is there any electron density along the internuclear axis? No. And so this is what's called a pi bond because there's no overlap in the internuclear axis. Pi bonds should be weaker than sigma bonds.
Those are all top views, right?
This is side view.
Side view. And the one on top.
This is any view. It could be side view again. The top view, you'd have to point this up like this. Look funny. Are you guys good?
Are you going to have to draw?
You just have to do more
energy diagram too?
Hmm?
Are you going to have to draw energy level diagram too?
Yes, you're going to have to draw the energy level diagram
Just
too.
showing you like which direction.
Yes. Yes, so the energy level diagram for the oxygen, let's go back and look at it. Now, can I erase this?
Can you do like an example, like with everything that you want in the test?
Right here. And so the energy level diagram is sp2 P. You have 2 lone pairs and 2 singles. And then the other oxygen comes in. The other oxygen comes in with an sp2, which is going to bond here, and a P, which is going to bond here. And so this one oxygen bonds in 2 places, therefore we call it a double bond. Do not do this. You know, this is a common mistake. Somebody will write the oxygen sp2 comes here, and a second oxygen P comes in here. Are there 2 different oxygens bonding? No, it's just one oxygen bonding in 2 places.
What? Why is it wrong?
Because it's the same oxygen given the electron. So you don't have to do a separate oxygen.
All right.
Can you do another example?
I don't want to,
Oh.
but I will.
We don't want to do a lot of things.
So you label everything P, P. Do you label the P orbitals like this? P, P?
Nope.
This, you know, if you did that, it makes it look like you have 2 different P orbitals, right? This whole thing is 1 P orbital. So you don't have to label it twice. This would be like calling this sp2 on the bottom and sp2 on the top and sp2 on the side. Does that make any sense? No. So don't do that either. You know, we don't want to have too many labels because now it looks like there's 5 orbitals. All right. Only 4. So, are you okay with this? What, you know what this tells us? Why do we do this?
Yeah, that's my question.
Why do we go through all the trouble? We go through all the trouble of doing this so that we could visualize what?
Electron density.
The electron density, the electron cloud.
And how does that, like, what can we infer?
And so how would you visualize the electron cloud on O2 to be like? You know? Well, the way I'd visualize it, we got some sp2 sigma bonding density here, electron cloud, right? We also got, which view do you want to do? Side view? Top view? Let's do the side view. We got electron cloud density from the lone pair here, and electron cloud density from the lone pair here. So electron cloud, right? And then we got the P pi bond. The pi bonding electron cloud density looks like what? This is side view. So basically we have 2 electrons worth of electron density in the purple, 2 electrons worth of electron density in the sigma here, and then the lone pair here, lone pair here, lone pair here, lone pair here. And so can you see kind of the electron cloud density? Visualize it?
So with the pi bond, you're showing us that there's no density with the electron cloud, no bond, no overlap, and
The internuclear
the
region.
internuclear region.
Yeah.
Okay.
Should be a pi bond less dense.
Pi bond less dense? What do you mean pi bond less dense? This is a pi
Less
bond.
electron cloud.
Less electron cloud?
It's the same problem.
We can't do that.
There's no overlap.
Like that? Here's the pi bond. You see what I'm doing here? That's the purple there. The sigma is the green here. This is the sp2 sigma. The lone pair is here. Another lone pair is here. Lone pair is here, and another lone pair is here. So we're mapping out the
I see it.
You see it?
I see it.
You
now.
see it?
Now
Good.
I did that.
Good.
It's clicking.
This is it. This is the side view. And so we're just trying to map out, we're trying to visualize the electron cloud density, right? So we can kind of get an idea of this. The reason we want this, actually, is it break time?
Yeah.
Yeah.
We'll take a break.